The next paper is entitled Incorporation of carbon 14 labeled alcohols during Fischer-Tropsch synthesis, Impact of Promoters on Iron Catalysts. It is authored by M.L. Tao, H. Tabak, S.Q. Bao, and E.H. Davis from the University of Louisville, and Professor Davis will be making the presentation.
This is complicated. Well, the title is what the contract was. The separating out the isotope effects has been so slow that I really will be talking just about one iron catalyst and some of the information that we got on olefin incorporation as well as on the double alpha question. With carbon 14, we have to do something slightly different than what you've heard about with carbon 13. If this is the synthesis scheme, you could have a C2 intermediate that could form the alkane or the alkene or an alcohol. What we do with carbon 14 is then label one of these compounds, add it with the synthesis gas, and then follow the incorporation as the reaction progresses. Today I'm going to concentrate on adding either alkene or alcohol. And as a schematic, if this alcohol builds in, one could visualize in the extreme some cases where now we're expressing the isotope per mole, the carbon 14 per mole. In this case, the carbon 14 compound is acting as a chain propagator, and so you would see the carbon 14 increase as you increase carbon number. If, on the other hand, the carbon 14 compound is acting only as an initiator, then you would expect the amount of carbon 14 per mole to stay constant with carbon number. One could assume that the alcohol would dehydrate to an olefin. This would undergo polymerization. Then you would see every even number for ethanol or ethylene, every even number increase. The odd number would have no carbon 14. If, for example, the carbon that you're adding in the tracer compound becomes equivalent to the CO, then you would have an increase in the carbon 14 per mole with carbon number. Emmett, working at atmospheric pressure, obtained examples for these two cases. In one, he was working with methanol, and the methanol decomposed under his conditions to give CO. The CO then, you see the increase in carbon 14 with carbon number as we expected. When he used alcohol at atmospheric pressure, with ethanol or propanol, Emmett got the result that you would expect if the alcohol, in this case ethanol, were acting as the initiator and then the CO was the chain propagator. The same thing with propanol. So that these results, however, were obtained at 1 atmosphere. We will be working at 7 atmospheres. The work that I will be describing today is work that we did at 7 atmospheres. First thing, we'll go through some of the results, somewhat qualitative, with the addition of olefins. The first is adding ethylene. What we did is the CO hydrogen mixture, we generate ethylene by dehydrating ethanol outside of the reactor. Now, unfortunately, we've never been able to get a totally clean catalyst in that we do get a small amount of C4 formed in generating the ethylene. But even so, we are able to see what happens to ethylene since we are adding 96 to 98% carbon 14 labeled ethylene. The ethylene can undergo two reactions. One is that it can be hydrogenated to the ethane, which is carbon-14 labeled. It could then serve as initiator and fit into form C3, C4, etc. What we observed is that of the ethylene that we added that reacted to that which was added, roughly 31% was converted. Of that which is converted, 75% was hydrogenated to ethane. The maximum amount that was incorporated was 25%. Of this 25%, a large fraction was in the C3. The amount of C4 impurity prevented us from accurately measuring that, but certainly we can say that the dominant amount of ethylene under these conditions would appear to carbonylate and form C3. It does not give you a large amount of building, not nearly as much as when we did with ethanol, that I'll show you later. Only about 6% of the added ethylene was incorporated into higher carbon numbers, and I say a significant fraction of this 6% goes to the C3 compound. However, the ethylene must absorb on the surface. It must have had the chance to incorporate because you get a significant fraction undergoing hydrogenation. The next olefin that I want to talk about gave even more surprising results. What I am showing here is a gas chromatograph for the hot trap sample. This is the cold trap. This is collected at about 10 degrees centigrade, and so this contains predominantly the C4, C5, C6, and then it starts falling off. But what we have added in this case is either the cis plus trans 2-pentene or the 1-pentene. These are the products that you observe in the GC. This is the cis, or the trans 2-pentene. This is cis 2-pentene. This is the reactant that we feed. It was labeled in both the 1 and 2 since it came from 3-pentanol. But if you observe, there is no detectable carbon-14 in the pentane, none of the C2 isomerized to give you the 1-pentene. So when we pass 2-pentene through it, essentially nothing has happened. This was surprising, so we synthesized 1-pentene. 1-pentene, the carbon-14 is shown in the bottom. I don't have the GC for these products, but it was essentially the same as this. If you notice the 1-pentene, you can barely detect the presence of either the cis or trans 2-pentene. Again, the absence of hydrogenation of pentene. And so, under our condition in a stirred tank reactor at 7 atmospheres, pentenes pass through the reactor essentially unconverted. When we put in decene, about 15% of the C10 olefin did undergo hydrogenation. A further 15% of it underwent isomerization. It did incorporate to a small extent. If we consider the C10 plus C11, and I do this because in liquid chromatography it was difficult to separate C11 from the large peak of C10 that we had. However, it does not appear that the C11 would have significantly increased the amount built in. So that 82% of the carbon-14 in the C10 to C15 ends up in this fraction. It indicates that a small amount builds in, but it is small. And so we have the case where with ethylene, we do have ethylene under these conditions undergoing conversion. The significant fraction of ethylene undergoes hydrogenation. A small fraction builds in, but it is predominantly in C3. The 1-pentene or the cis or trans 2-pentene essentially undergo no detectable reaction. With the decene, about 15% of it is hydrogenated, about 15% undergoes isomerization to other C10 olefins, and so it is being absorbed. It's having the chance to incorporate, but again, a small amount is all it does incorporate. And so if we look at the product distribution of olefin to alkane, or alkene to alkane ratio, this is the fraction of alkene formed, alkene divided by the alkene plus alkene per carbon number. If you look at C2, a high fraction of that is alkane. Now, the reason it appears that this is high in alkane is that the ethylene that is formed can undergo hydrogenation. When we put C5 in, it undergoes very little conversion. The C10 is hydrogenating, and presumably this curve increases in fraction of alkane because of hydrogenation of the primary products, which are alkenes. And so the carbon-14 would say that we are forming as primary products with this doubly promoted iron catalyst predominantly alkenes. The reason that you get a high fraction of alkane at the low carbon number and again at the high carbon number is hydrogenation. The hydrogenation in these higher hydrocarbons is probably due to longer retention time in the reactor. The other thing that I want to cover is the question of the double alpha value. This is plots from Anderson's book. 4 different catalysts. This is work that was done in Germany in the 40s. And there is a decided break in the Anderson-Schultz fluorine plot at around carbon number 10. These are 4 different catalysts. Standard, well, Exxon now, did this in fluid bed. They also get a break when they plot so that they are getting the double alpha value. I don't know that Satterfield was the first to make a plot like this, but at least his was nice and convenient, and so that's the one I will show. If we look at the compound class, the red is the oxygenate, which is predominantly alcohol. The green represents the alkenes, and then this is the alkane and the total carbon number fraction. So the reason by compound class that you're getting the 2 alphas appear to be the increased amount of paraffin that you get in the higher carbon number. A large number of people have observed this 2 alpha value. The break for a variety of catalysts occur roughly in the same position. The work that I'm going to describe, well, let me show you. I changed the order since they talked about alkene incorporation today. This is a schematic of the apparatus for doing the alcohol addition. We have the carbon monoxide hydrogen feed. The flow rate is controlled. When we desire to incorporate carbon-14 compound, we add it as a pump into the CO hydrogen feed. It goes to a 1 liter stirred tank autoclave. This is collected first in the hot trap, which is maintained roughly 55-60 degrees centigrade. Then in a cold trap, which is maintained at 10. We take the gas sample directly to a gas analyzer and then to a proportional counter so that we analyze the gas directly as it's formed. And we get, in addition to the gas composition, we measure on a proportional counter the amount of carbon-14 present in each peak as it elutes from the GC. It'll be easier to read this than it is to get it apart. The catalyst was a doubly promoted C73, which a lot of people have used, 260 degrees centigrade, 100 pounds total pressure. CO to hydrogen ratio of 0.8, space velocity of 180 cc's per hour per gram of iron. The reactor is run as a slurry reactor with the catalyst suspended in octocosane. A schematic of the analysis is that a GC, the products from this goes to the proportional counter. An example for A containing no carbon-14, B containing carbon-14. The GC would show you 2 peaks for A and B, but only peak B would have carbon-14 in it. And so this is the way that we detect in the gas sample the amount of carbon-14. In order to carry out the analysis, we found it was more complicated than a packed column could handle. And so we separate using dry silica gel chromatography into an alkene and an alkene fraction. And so we are analyzing the carbon-14 in the liquid products, in the alkane, and in the alkene fraction. The products that we got give the typical 2 alpha value plot. The first one is smaller number than the second. The reason that this falls off is that these are high carbon numbers. They are being retained in the C28 solvent and have not attained equilibrium in coming out of the reactor yet. If we look at the carbon-14 in just by carbon number in the products, when we add pentanol, which has carbon-14, we see only significant amount of carbon-14 in C5 and higher. This is the gas sample, and so we're limited to about 7 carbon numbers in the gas sample. But CO, C3, C4 have a low carbon-14 per mole relative to the C5. You will see that this C5 really should be a little higher because we're including an iso C5 which does not contain carbon-14. If we look at the carbon-14 where we separate the C5s, you will see this much better. The normal pentane has this carbon-14 per mole. The alkenes, the 2-methylbutane has below our detectable limit of carbon-14, saying, for one thing, that the C5 normal is not undergoing isomerization. Otherwise, it would contain this amount of carbon-14. It does appear that some of the alcohol is undergoing hydrogenation or hydrogenolysis directly to C5 alkane because it does have an appreciably higher carbon-14 per mole than do the butenes. And so apparently some of this is being converted directly. Other is going to form the olefin, which appears as a product. Now, in addition to the gas phase olefins, which those C5s are inert, we've already shown by adding the olefins they're inert, there is carbon-14 incorporated into higher carbon numbers when we add the alcohol. Presumably, this must be incorporated without coming off of the surface. When we put the C6 alkane and alkene on the same basis, we see that we get a plot very similar to what Satterfield did. The olefins follow a single alpha value, but the alkenes follow 2 alpha values. When we look at the carbon-14 per mole, we see an even more surprising effect. The olefins contain significantly more carbon-14 per mole than do the alkanes. Now, there's no way that you can hydrogenate this alkane and get a lower amount of carbon-14 in the paraffin. Remember, we're running this reaction in a stir tank reactor. We're running for 24 hours. We do accumulate the higher hydrocarbons in the reactor. And so we are going to be putting in, at this time, the carbon-14. each carbon is going, the carbon-14 labeled compound will accumulate. You can take into account the accumulation by using the experimental composition by carbon number of a sample withdrawn directly from the reactor at the time we do the experiment to evaluate what theta is. This is the amount of that alkane accumulated in the reactor. This is then time over the 24-hour period. To show you that this does accumulate, we have taken a sample directly from the reactor. The composition of the product that we take from the reactor is this. We take the value of this, the amount formed, this becomes theta, and we correct for the accumulation. Now, when we do this for the alkenes, we have calculated how much accumulation of alkenes by carbon number would decrease the carbon-14. What we are showing here is if we assume that you get equal carbon-14 per mole for all of these carbon numbers and the alkenes, and then we correct it for the amount of alkene that has accumulated in the reactor, this correction will move the experimental point, the point that should be here. Let me back up. The experimental point is the circle. The calculated point, assuming a constant carbon-14 but a dilution because of accumulation, then the squares become the calculated. So for the alkenes, accumulation accounts for the deviation from this expected behavior of having constant carbon-14 per mole. When we go to the alkenes, we see a different situation. If we make the same correction for the alkanes, assume a constant carbon-14 per mole in the alkanes that are formed during the 24-hour period, correct them for the amount of alkanes that have accumulated in the reactor. That moves it to this point. So the squares are the same correction that we use for the alkenes. In the case of alkenes, that was adequate. In the case of alkanes, it is totally inadequate to account for the dilution. If, on the other hand, we make a second correction, and the second one is to take into consideration two alphas, which are totally independent and which carbon from one cannot exchange with carbon from the other. The first one produces carbon-14 labeled compounds. They produce the alkanes, alkenes, and oxygenates. The second one produces only paraffins without carbon-14. If we make those two assumptions and use the alpha values that we calculated, or that we obtained experimentally, so that we correct first for accumulation, and then we correct for the two alpha values, one of which produces paraffins only without carbon-14, then the accumulation gets you here, the two alpha value gives you these calculated values. And so the two corrections will get you to the experimental data. To show you that what we are starting out with, we would say that this agrees with the alcohol initiating, giving you constant value. If we look at the gas sample, we get the, we get a constant carbon-14 per mole from C2 through C4, with this one being present in a small amount and probably a significant experimental error. But the gas samples with ethanol give you the thing that you would expect if the alcohol initiated a reaction. We get the same thing with the higher carbon numbers. If we assume that olefins accumulate, that correction takes care of the olefins, but not the alkanes. I should at least show you one figure, since he says I'm about out of time, that will convince you that there are alkanes being formed that do not contain carbon-14. The top is or the bottom is the gas chromatograph. This is the C5 region, C6. This is when we're adding carbon-14 labeled pentanol. This is a different column in which this would be the alkane and the alkene for the C6. This is a compound that at the time we did this, we didn't recognize what we had, so we didn't make an effort to identify this gas sample. And a year later, we don't have it. But this is an alkene. It's in a region that an oxygenate that we have detected does not occur. And if you look at the proportional counter, this peak is larger than the normal C6 peak. The carbon-14 in the C6 is here. In this compound, which is some iso C6 in all likelihood, has essentially no carbon-14. And so we have indeed detected alkanes which do not have carbon-14. Finally, I guess I should acknowledge the ones who paid the bill, or you don't get to acknowledge them again. And so this was supported by DOE and by the Kentucky Energy Cabinet. Thank you.
Thank you very much, and we'll open the paper for discussions or questions.
Van Nuys, Penn State. Burt, have you had time enough to consider trying to, if you do have these two pools of carbon on the surface, one incorporating the labeled compound and one that doesn't, have you had any chance to vary any of the parameters or change the catalyst to see if you can shift those pools to vary those alpha times?
This is what we are starting to do now. We have run iron on silicon. We did this before we had developed the liquid chromatographic analysis to do the higher carbon numbers. I might say that we get very similar results whether we start with ethanol or C5 or C10 alcohols with the C73 catalyst, with the higher carbon numbers. All of them give an activity that appears to decrease. But we haven't looked at other promoters at this point.
What are the promoters in there? Maybe you mentioned right at the beginning.
It's a commercial catalyst, and they have about 3 different alkali promoters, one of which is calcium and potassium and some amount of sodium. There's another one that I don't remember offhand. The structural promoter is predominantly aluminum and silicon. I don't think it has silicon. It has just aluminum.
Okay, we have time for one more quick question. No more. Thank you very much.